be on.
One, two, three. Okay. Oh, yes, green light.
Okay, take a seat, everyone, please. We'll get started in just a moment. Push back a little bit, give you guys a little bit more time for the break there. We will make up the time at the end of the day. Next, I wanted to introduce Alex Aizman from Nexenta. He's going to be talking about ZFS writeback caching. So this is kind of in contrast to some of the things that we heard about earlier today, which are a little bit more targeted, quick fixes for some low-hanging fruit. This is, excuse me, this is kind of taking a big swing at a big problem. So I'm interested to hear about how you guys have approached this.
Guys, thanks for the opportunity. Appreciate it very much. So basically, it's like I say, on this slide is a missing piece. If you look at local distributed block files, object, whatever, write-back cache is write cache for that matter is almost ubiquitous checklist item, and the reason is simple: it's kind of needed very often, right? For me, it kind of tracks back to 2012, where I was this old place, Nexenta place, on Mountain View, Custer Street, and we just started to run those VDI workloads, 100 desktops, big joy, and we just stared in utter disbelief on those spikes. Well, it's a bit of dramatization, but yes, it's kind of characteristical spikes down every so often, a few seconds, give or take, right? And ultimately, write performance like 3 times worse. Right? So what do we do? First thing that we did, go through available options. That's slog. Let's take just greatest, latest SSDs, right? Didn't help a bit. Next thing that we did actually at this point was what we called metadata offload. We started to store metadata on SSDs. Just got out of this, few percentage points, not much at all. And then we started on this one. The project is 2 years of life. Couple bullet points here. All flash. What's the connection? The connection is, I think I can talk later about it, but basically, you take one SSD, you get 100K IOPS, 500 megabytes, maybe 4 throughput. You add another couple, ZFS doesn't scale anymore, right? And so, what does it mean? It means that basically the idea here is to kind of improve it overall, but not trying to hit this 1 million IOPS goal, because those type goals, basically they involve inevitable trade-offs and sacrifices. So the idea for this project, kind of overall, and I'm gonna maybe reiterate it in different words later, it's what I call combinational, maybe multi-factor optimization, right? No sacrifices at all. Every single feature of the ZFS checklist, unlimited snapshot, you name it, plus write cache that gives better performance on bigger capacities. Virtualization is connected a little bit. Actually, there is a bigger umbrella item on this one. It's you have any kind of clustered infrastructure with one use servers tightly packing this one, those racks and rows. Right, and the real estate on those is very expensive, and you have, there are no wires, everything is optimized out, and you have a couple drives, maybe, right? And you want to use those drives for caching, and not only for read caching, right, as well. So, and virtualization is, of course, enabler of this one. Now, the core, topic inside write cache mechanism that we have here is ability to migrate data, of course. Right? So it's a live data, the same zpool version 28 format that you have an upstream, right? But it moves in the background and transparently. And so basically this stuff is called sublime data migration. It tracks back historically. Early 2000s, you might remember Comparent, 3PAR, both acquired at this point. Comparent called it data progression. Basically, this core capability to move data transparently without degrading performance and without endangering consistency, integrity of the data, is the one that sits underneath those kind of go-to-market business, quote-unquote, applications and use cases. Right? There is ILM, HSM applications. There is rebalancing from failing devices. There is device removal, of course, SLA, dynamic support for user service level agreements, and so on and so forth. So the point is that once you can move data, you can actually move data for any other reason. Now, just to give you a snapshot immediately, I have very little time, so I'm going to kind of try to move fast here. So, very familiar, right? The OpenZFS commands, right? The novelty here is the special keyboard. Now, think about slog. Slog is probably as old as ZFS itself, maybe as new as ZFS itself, right? And the idea behind slog was that it's a new type of VDEF, right? From where you can allocate, in case of slog, ZIL records, right? And specialists as well, the same kind of idea. It's a new type of VDEF, new metaslab class, from where we can allocate storage, right? There's one little item here that when you provision pool with special VDEF, which by the way supports the same type of configurations as log itself, by default you get ZIL on it as well, right? Which kind of makes sense because the SSDs are kind of the same required SSDs, right? Optimized, great render performance, endurance, and whatnot, right? But certainly you can have your own separate slog if you want, although I don't know why, right? Same device manipulation on this one. There is a certain feature, total compliance with ZFS, called write cache, and unless you have special VDEF on the device, you don't. This feature is disabled. You don't use it, and certainly no. And the window on the second half of the slide is basically, the idea here is that we can set write cache on specific data sets. So right now this setting is forcefully recursive, but for only one reason, that we didn't have time to make it not recursive. And really, I don't know why exactly user would make it on a single data set yet, but it's doable, right? So the point is that you can have multiple choices. Some data sets may be write cache, some data sets that not important, write-wise, maybe not. So what is write cache? This slide touches on several issues. Kind of difficult for me it's going to be to talk about it because there is a mind switch between 1 and 2 and 3 and 4 and 5, right? So number one, user just adds a couple of SSDs. In any supported configuration, think as log here, as a special VDEF. Now you have a separate metaslab, right, on this pool, inside this pool, right, that will serve for write cache and serve as metadata storage as well, frankly. This is just a default setting for us, although this metadata storage and write caching are totally orthogonal and unrelated. Different set of tunables and no dependencies. Now, bullets 2 and 3, here we have a little bit of kind of step aside. So think about block pointer, right? 128 bytes, 3 DVAs. So what write cache does, it introduces new convention on the usage of those virtual addresses. Well, not so much virtual as Jeff just explained to us. So the convention is that the first DVA, DVA 0, is allocated from SSDs effectively, and the second DVA, DVA 1, is allocated from normal class, right? And third DVA is not used. That's how we do it now. And there are multiple variations. This stuff can be swapped around and so on, but that's how it underwent through rigorous stress and whatever. It's right now stable code in our case. And so this bullet number 2 is the IO stage, when we DVA allocate stage effectively. We allocate it in a certain way without changing format again. We just allocate it from both in one shot, right? From both classes in one shot. Now, why it is important? By the way, just this asterisk Matt Arons, back when then, 2-3 years, we had several kind of venues into this topic, talked to Matt about it, And I think Matt pronounced this kind of pre-allocation first. So credit goes to. Now, why it is important? Again, I may not have time to can explain it fully, but the greatest, biggest kind of feature, biggest effect of this is that content remains immutable as a result of this of the subsequent migration of data, right? The fact that we pre-allocate allows us to keep it totally intact, unchanged, right? That's actually great. That's basically this simple kind of statement goes way beyond and outside ZFS. I'm doing some other projects right now with distributed clusters where we have this referential integrity and content traceability, and there you need to transform and move data as well for the same kind of reasons that we have in local file systems. And there we have this kind of immutable situation as well. It's a very important point here. And this is the one that I think ultimately makes it feasible and successful. And so then bullet number 3, that's the writing stage of the ZIO pipeline, where we write only to effectively SSDs, right? Then 4 and 5, that's actually migration itself. Write cache has a couple of its own threads. It has a bunch of task queues allocated, pre-allocated, and we basically collect and move data gradually in so-called windows. So what's the write cache window and migration steps? Write cache window is a very simple thing. It's defined by 2 transaction group numbers. Right? When the pool gets created, we have this, its age is 4, happens to be. Right? So the very first window, if write cache at this point exists, enabled, on any of the data sets, the very first window is going to be 4 and something. And the next window is going to be something plus 1 and something else. Right? So that's how gradually kind of goes in the same direction as TXGs themselves. Right? That's essentially item number 1. 2 and 3 done in parallel. We are collecting and we are moving, collecting and moving, collecting and moving. And this kind of converges when we are inside this window. We have collected all the data blocks and moved them all. Right? All this time during this process, the reading is done through this logic from flush. Right? Once we reach the end of the window, we start freeing. At this point, we basically start reading from just hard drives, effectively, normal class. And we close that's number 4, closing the window. And effectively, the only thing that is done in syncing context is kind of step number 4, where we write into ZAP, into MOS, the fact that this window is closed, and free all the DVA zeros. To free, we don't use ZIOs. We actually just directly free them. And again, nothing is changed as a result of this operation. So this one is a kind of visualization of the window, which is this exact kind of green boundaries rectangle in the center of the picture. In this case, it shows 6 blocks. In our case, we deal typically with in benchmarks and stress tests with a few millions of those, right? And then there are 4 different layouts of block pointers. Top left, for instance, is older block, right? That's already has been migrated, and is happily sitting on pre-allocated. Remember pre-allocation of those pointers on hard drives, normal class, right? Whatever it is. At the right top, right, shows the reverse, right? It's a fresh write, for instance, happened, fresh block, not so much time ago. Right? The layout reflects here that the valid pointer on it is the DVA 0. Therefore, we are going to be reading it from flush. And then there is some in-between scenarios within the window, right? And so some of them, we pick up and copy. Some of them, at some point later, we start freeing a situation, and we kind of, need to support all these scenarios. Now, I should say that write cache kind of fits very nicely into ZFS code. It's something that does not distribute itself across layers and pieces of code and so on. It's quite compact in its impact. For instance, as far as the IO pipeline, we touch exactly on 2 stages and only 2 stages. Those are highlighted here, right? And the reading writing, the writing stage certainly touches on, we have some code inside DBA allocator, already mentioned this. And both read and write have some logic inside. VDF mirror start stage. Nothing else was needed to be changed, which is kind of nice. Right, so writing also visualized here, a nice picture. Something happens prior to, on a pool where you have special VDF, and at least one data set is write cache on, right? Something happens before actual ZIO pipeline, and that is DME write policy looks at a data set that we are writing to, right? And if this data set is write cache on, then this knowledge is propagated into ZIO props and then down the stack. Right? This kind of information will follow on through ZIO DBA allocate and VDF mirror start stages. It does not necessarily mean that we absolutely will write cache this block, but it means that we may write cache this block. Later, this left side of the picture, where we actually allocate actual blocks, right? And the interesting point here is that at this point we load balance. It never changes. When you have choices, as far as, for instance, if you have 2 disks and you have a choice on which to run, to write or to read, right? Or if you have hundreds nodes in a distributed cluster and you have a choice, you want the one target that is least loaded and will perform the operation faster. And that's exactly what we do here. And it's actually put here actual function call select class, where we look at basically I start like statistics. There are 2 different mechanisms how to look at these statistics, but the idea is that we cannot allow ourselves to make any assumptions on. Remember, Nexenta is a software appliance company. We don't make assumptions. We don't know what's the ratio between flash and hard drives. We don't know what's the platform. We don't know. We cannot make any kind of block sizes. Read write rate. We cannot make any kind of simplifying assumptions here. Therefore, we look at runtime. We load balance at runtime. Right. And so, if this load balancing piece decides that it does make sense, it is more optimal to write to special VDF, then basically we do allocate it in such a way, shown on the left side. I showed it already a couple times, this new layout of block pointer, but without changing any bits on the block pointer itself, and we write to DBA 0. That's the that's VDF start stage. So that sounds simple so far, but it's a tricky simplicity. The project took 2 years, like I said, at least 2 years. And we need to resolve a whole bunch of anything and everything you can think of. From where to read, I already named this kind of puzzle. When to free and how to do it safe, right? Because remember, you have another kind of workload running gradually on a live array. This is a live storage, right? No restrictions, no limitations, no nothing. For instance, bullet number 4 is kind of interesting here. We'll not have time to talk about it, but talks about aggregating of those pre-allocated spaces on hard drives. Recall that the MetaSlab basically tries to, on one hand, spread the load across VDFs. On the other hand, it tries to have enough VDF writing to aggregate enough on a per VDF base, right? But in this case, basically we take blocks from normal class, right? But we don't. Sometimes we write them, sometimes we don't, right? Sometimes we do it later, right? So that's a subtle point as far as questions will be answered later, basically on this one. This is, everything that I show here is effectively resolved. Running out of space, of course. The first thing that you think about, when you have a separate MetaSlab class, and a couple or smaller space for it, what if you run out of space? There are a couple thresholds and so on. To handle this, so take your time maybe to read through this, and each of these is a separate puzzle right now resolved. And this is just a small subset of what needed to be resolved. Reading. So on the reading side, you have two kind of major ifs, forks. First of all, the reader must determine whether this block is special. Special in the sense that this special layout. Remember this DVA0, DVA1, left and right sides of this pool, special normal, right? Is it like this? Because certainly load balancer, whatnot, we never know. It's dynamic kind of feature. So here I need to say that right now what we have in stable code, and when I say stable code, I mean Nixenta Store version 5 that is looking into Q1, hopefully, right? So what we have in stable code is derives this information without using any bits on the block pointer itself. Right? We just look into DVAs themselves, frankly, right? But the price for it is actually SPA config enter, SPA config exit. And it's a small price. I don't remember it showing up in flame graphs and dtraces, but I'll still, we already have this code, and we'll still try to compare whether it makes sense to take one of the 129 actually free bits on block pointer. There are two paddings, 64-bit, and there is one unused compression, encryption. So that's the determining whether this a given block that is being read is special or not. If it is special, then we look at this. Remember this write cache window, 2 TXG numbers, right? So if and this is kind of a little bit outdated slide here, because we will continue reading it until the very time when we start freeing this write cache window and closing this, moving on. So this one is, I have a couple of those. And by the way, I have a bunch of backup slides that I will not have time to talk about. It's just a piece of configuration tunables here, just to give you another kind of perspective, what it is about, all this stuff. So this, the very first tunable, is by default, by default is this throughput load balancer. We have another piece of code that can load balance based on aggregated latencies. Remember this, we aggregate those statistics across classes, right? And so for us to understand where to write faster, we need to look at the class as a whole, right? That's what we do, periodically. And when we need to change the ratio of how much goes to where, we actually do it. So one future development could be kind of combining this, actually removing this. I would dream to actually at some point remove this knob static altogether, because the system must be capable of kind of adjusting on the fly based on I/O pattern of user workload. But right now it's like this. Plus a few related variables here, certain thresholds, and so on. Some other stuff. At the bottom you have again left column at the bottom you have a couple of variables, more than a couple of variables related to cancellation. So what if user rewrites data faster than we move it? At some point it kind of becomes not worth it, right? Because let's say in this case we have configuration that if user rewrote or deleted 20% of data and there is no snapshot that holds it, right? Why do we need to move it? It's going to disappear anyway. So what we do is we cancel the window, remove free this stuff that sits in memory in AVL trees that we maintain for write cache, and basically just move the right boundary of the window to the right. This one is kind of infographic. At a glance kind of thing, at some point the only reason I have it here is just to remind myself that there is a bunch of backup slides. That's number one. Number two, basically if I have 4 hours, some such time, we could just go and touch every functional piece here. What is the cause and what's the effect of this, and what happens when, and so on and so forth. Again, the idea here is that if you want kind of in depth, you can look just on one, piece of information. Everything is mostly here. Now, performance benchmark. I'm not sure how much time I have, but okay, great. So performance benchmark. This is one of those benchmarks where we kind of do it across the board. Read-write ratios, we do block sizes, record sizes, we do asynchronous, synchronous, read, modify, write, and stuff. And kind of it's comprehensive more or less. Exactly enumerated hardwares here. And we run hundreds and hundreds of benchmarks. Some of them are interesting in the sense that basically the one thing that to pay attention, well, as far as write cache is to ratio between hard drives and SSDs, of course, and to see how load balancer actually is capable to optimize for any kind of configuration. So in this case, this is just 2, right? 4 hard drives and 2 SSDs for special VDEV. Now, so lots of numbers here. Like I said, couple record sizes, 16 and 128. Transfer size or user level block size, right? It's 16K, which means read, modify, write on the bottom side of the table, this entire bottom. And 3 types of kind of workload: sequential write, sequential rewrite, and random, totally random. Very, very stressful. And if you look, if you compare kind of green numbers, and again, this is the same apples to apples hardwares, right? Except that this is NFS, 2 NFS clients. In one case, the same SSDs are used for ZIL naturally, because NFS is writes synchronously most of the time, or quite a bit, right? And in other kind of back-to-back benchmark comparison, the same exact SSDs are just used for write cache. That's all, right? So basically, you have just software difference here, nothing else. It's a software difference. And so if you see here, basically on kind of sequential side of things, it's kind of 50% more or less performance improvement. On the random side, it's kind of from 3 times to like 6 and more times improvement, right? Just out of the pure software magic, right? Few graphics that we just plotted out of GNU plotted effectively out of those experiments. Much more available. All these information and details you may want to ask. The purple thing here is is regular kind of vanilla ZFS, and the green one is the one that's done measured from write cache. And asynchronous writes, kind of more or less the same picture, right? You don't see much of the difference between synchronous and asynchronous in this case. But remember, this there is a little bit of unfair advantage. Not unfair, it's totally fair. But when we say this, those green rows, right? When we say write cache, we actually use write cache for both. Not write cache, but this special VDEV by default will provide both ZIL and write cache as well. L2ARC certainly is different. So in this case, asynchronous write, there is no ZIL in play at all, right? So in this case, the same SSDs are used just for memory, level 2. And again, basically, you see the performance. Performance is improved, definitely. And the pictures. I especially like this 50% read-write kind of picture, where basically this is what you want to have. You don't want spikes, right? Even if those spikes kind of higher, more or less, floating, right? This is more streamlined. This example, by the way, is read, modify, write example, because record size 128 and transfer size is 16. What's next? There is a bunch of stuff that is sitting on our private repositories and outside this Nexenta Store 5.0, just because there is no time to kind of push on it, frankly. And so write cache is this migration traffic, new type of workload, right? This coincides with everything else that's going on. It kind of makes sense, like from just kind of common sense perspective. makes sense to have its own VDF queue, its own priority queue for it, right? It's an easy code. It's already done. The order of priorities to us seems to be like this: sync, async, write cache, and scrub. That kind of makes sense to us. And then you have this ability to separately configure min-max. Right? Depends on your hardwares and stuff. That's one done. The second bullet is almost done. I'm not sure that we need to insist on non-recursive write cache property on data sets. But this certainly is not my call, it's customers. Now, what can be optimized? That's the second box here. Right now, what we do, we use this much of ZFS for write cache without change. Right? And traversal, zpool traverse is one of those. Traverse pool, rather, that calls traverse visit BPs in quite recursive fashion. And so, yes, we could easily maybe optimize this one. Just because I remember this write cache, it does only data blocks, Because the metadata is separate bits. First of all, it's much smaller, and the second of all, it's a separate set of tunables, etc. And then I already talked about block pointer knowing itself that it's special. Not, right now we have this totally like zero information. We just detect based on its layout. Right? This is already almost done. Now this third box, right? Write cache reinforces this kind of need to have per class kind of hot sparing, right? Because slog has the same, we just disable it for slog. But basically, you want to have this hot spare sitting separately and waiting if we need to replace one of those SSDs. Right? Key startup observability. Couple other items, maybe. The last box here talks about kind of maybe more kind of remote future, and this more of research. For instance, this tiering called hot migration. The fact that we can move data from special to normal classes, right? Also means that if need be, we can easily move it kind of backwards, right? So if in fact it becomes hot, if this working set that user is right now is loading and updating and working with, is kind of keeps it hot and arc, right? Why don't we kind of move it backwards? That's much later maybe. Ultimately, it's all absolutely possible at this point. So again, the point of this write cache project is absolutely a combination of things. It's performance and capacity both. It's an idea that you have this hundreds of terabytes of storage on let's say SATA, cheap stuff, right? And a couple of SSDs on it, and you get SSD-like performance. Acknowledgements. I already mentioned Matt. For me, Matt is absolutely source of this continuity and context. I need to say that these two guys, Alex Dater and Roman Strashkin, there are always many people, right? But these two, they were standing through hell and high water. This one, it's a non-trivial project. So I absolutely want to acknowledge and recognize this contribution of these two guys. Questions? Sure.
Sorry
about that.
Questions, that's all right. Catch Alex afterwards. Thanks for really interesting ideas about how we should take ZFS performance forwards.
Absolutely. Thank you.